In our last video, we learned about truth tables and how they can be used to determine if two statements are logically equivalent. In this video, we're going to extend that idea to think about how to construct a truth table for a proposition that has a more complicated structure than just a basic connective. We ended the last video wondering about if P then Q and its contrapositive, which is if not Q then not P. Let's build a truth table for that contrapositive and see if it's really logically equivalent to the original. Making this truth table is going to be a little harder this time because more is happening in the contrapositive than just switching the hypothesis and conclusion. There are two intermediate steps. First, we negate the hypothesis, and then we negate the conclusion, and then we switch them. In order to keep careful track of what's happening, in the truth table for the contrapositive, I'm going to create columns for the atomic statements P and Q, and then a column for the final proposition, if not Q, then not P. But I'm also going to create two other columns, one for each of the intermediate steps, negating P and negating Q. Just as in the last video, I'll make one row for each of the combinations of truth values of the inputs. I'll put these in the same order as we did then. Next, rather than look directly at the final proposition, I'll do the intermediate steps first. In the column for not P, I'm just looking at the truth value for P and writing down its opposite. And then I'll do the same thing in the column for not Q. And now I'm looking at the contrapositive. This has not Q as the hypothesis and not P as the conclusion. Remembering that a conditional statement is true in all cases except where the hypothesis, which this time is not Q, is true, but the conclusion, which is not P this time, is false, I can see that the final proposition is false in this row, where again, not Q is true, but not P is false. In all other rows, either the hypothesis is false, as in rows 1 and 3, or both the hypothesis and the conclusion are true in row 4. So those result in true. Now looking back at the truth table for if P then Q, I can see that the outputs are the same in each possible combination of truth values. This means that every conditional statement is logically equivalent to its contrapositive. So making a truth table for a complex proposition is a little like doing an arithmetic calculation with a lot of parentheses and operations involved. In this calculation here, for example, we use natural order of operations to do the computations in parentheses first, then the exponents, then the multiplication, and finally the addition. We build up the computation from the lowest level gradually to the highest level. Similarly, when making a truth table for a proposition with a lot of parts, we work from the lowest level and gradually assemble the entire proposition using separate columns in the truth table to keep track of the intermediate steps. Let's look at another example, not P or Q. Let's set up the rows and columns of this truth table. First, there's two columns for the input variables P and Q. Now, building from the lowest level up, I'm going to need a column for not P, then a column for the final statement, not P or Q. Pause the video here and see if you can fill in the rest of this truth table. We put in 4 rows for the combinations of truth values of two variables, like so. We fill in the truth table from the lowest level first. That's not P, which is just the opposite of whatever truth value P has. Now, to get to that last column, we remember that a disjunction is true when one or both of the parts is true. That means we should put false here in row 2 and true everywhere else. So here is the final result. And if that looks familiar, then you're paying attention because this is the same truth table as if P then Q. That means that if P then Q is logically equivalent to not P or Q. And that's why when we looked at logic gates earlier, we didn't see one for a conditional statement. It's because we didn't need one. We can just chain together the logic gate for not with a logic gate for or. Now let's look at one more example. You might have wondered in the last example whether the parentheses around not P were necessary. Well, if you leave them off, you get this, which might be interpreted as not P or Q. That is the negation of the entire statement P or Q. Now, is that statement logically equivalent to not P or Q? Pause the video and make a truth table for not P or Q and find out. To set up the truth table, as always, we'll include 2 columns for the input variables. This time there's still an intermediate step, but it's to form P or Q first. Then the final step is to negate the statement P or Q. As before, there are 2 inputs, so that's 4 combinations of truth values, and we'll put those in as we've been doing. Now let's work from the bottom up. First, look at P or Q. This is a basic disjunction, and so this will have a false here in row 4 and true elsewhere. Now in the final column, we're going to negate all of that, so we simply flip the truth values to get false, 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 true. This is a complete and correct truth table, and you'll notice it's definitely not the same as the truth table for not P or Q. So those 2 statements are not logically equivalent, which tells us that the parentheses really do matter here. So in this video and in the last one, you learned how to make a truth table for a logical proposition with 2 atomic inputs, even when there are intermediate steps involved, and how to use those truth tables to determine logical equivalence of propositions. The next video is one more look at truth tables, and we'll raise the complexity to look at propositions with multiple intermediate steps, as well as those with 3 and even 4 input variables.